In this work, we propose a framework for physical human-robot-human interaction during gait rehabilitation, where a physical therapist wears an IMU suit and a patient with sensory motor impairments wears an exoskeleton. To virtually connect the therapist and patient, we render a unidirectional interaction between the IMU and exoskeleton joint angles. The therapist can modify their own leg movements to apply corrections to the patient's movements without predefined exoskeleton trajectories. This allows the therapist to use their expertise to intuitively adapt to each patient's impairments and facilitates unstructured rehabilitation scenarios like training with obstacle avoidance. To implement the virtual interaction between therapist and patient, we propose an impedance control designed in the frequency domain, targeting specific movement frequencies for different patients and training types. The impedance profile is a one-pole, one-zero transfer function, which corresponds to a stiffness at low frequencies, a stiffness at high frequencies, and a cutoff frequency for the transition between the stiffnesses. The frequency response can be dynamically adjusted during rehabilitation, as the therapist may change these parameters according to the patient's level of impairment. This proposed control offers more support and guidance for slow, deliberate movements that are typical of a patient performing exercises. At the same time, this impedance profile smooths quick and abrupt movements, which can be uncomfortable and even dangerous for the patient. This impedance control was integrated in a whole exoskeleton closed-loop compensation controller developed previously that compensates for the exoskeleton's friction and gravity. The framework was validated in a pair of healthy users, a teacher wearing an IMU suit and a student wearing a 6 degree of freedom exoskeleton. We tested 3 scenarios to demonstrate how this approach can provide haptic cues at multiple contact points for both repetitive and unstructured rehabilitation exercises. In all 3 scenarios, the users were asked to walk on 2 different treadmills without seeing each other. In the first scenario, we tested the effect of the virtual connection stiffness on teacher-student interaction during natural walking. The 2 users were asked to walk at 1.1 kilometers per hour, while 3 interaction impedances were applied to the exoskeleton controller: no interaction, soft interaction, and stiff interaction. We hypothesized that stiffer connections would more closely align the joint configurations of the student and teacher. For this reason, the correlation between the joint kinematics of the 2 users was evaluated in all conditions. This video demonstrates the walking patterns of the 2 users without the virtual interaction. Here, there is no correlation between the 2 users due to a lack of synchronization and different step frequencies, as no haptic cues were transmitted. In this video, we show the walking patterns of the 2 users while rendering the virtual connection. While walking, the designed interaction control commands non-zero interaction torques, which are felt by the student wearing the exoskeleton. In the soft interaction, this results in higher correlation between the joint kinematics of the 2 users, as their trajectories are more synchronized at the hip, knee, and ankle. Increasing the stiffness of the connection results in higher correlation between the users, particularly at the hip and knee, due to larger torques experienced by the student. These results suggest that the interaction control can transfer haptic cues of the desired walking pattern from the teacher to the student, depending on the stiffness of the connection. In the second scenario, we use the stiff interaction to demonstrate how the teacher can transfer an asymmetric walking pattern to the student. While walking on the treadmill, the teacher exaggerated the movements of the left leg compared to the right. The student was instructed to follow the haptic forces they experienced. In just a few steps, the virtual interaction allowed the student to perceive and adopt the asymmetric gait pattern, without visual feedback of the teacher or prior knowledge of this new pattern. In a rehabilitation scenario, this framework could allow a therapist to naturally transition between different rehabilitation exercises, such as overground walking to stairs, while providing multi-joint assistance to their patient. In the third scenario, the stiff virtual interaction was evaluated during an obstacle avoidance task. The teacher stepped over randomly placed physical obstacles, while the student was asked to follow the suggested movements. These physical obstacles were perceived by the student as random variations in the natural gait pattern. Foot clearance was compared between the users to investigate if the interaction could promptly induce changes in the student's gait pattern when random events were encountered. As seen in the video, the increased foot clearance was matched by the student, while relying only on the haptic feedback. This scenario can be useful in unstructured rehabilitation exercises that are difficult to facilitate with exoskeletons using predefined trajectories. Introducing obstacles to the therapist's path can transmit forces to the patients that we refer to as virtual obstacles. Such an approach can promote movement variability without interacting with physical obstacles that could pose a risk to the patient.